The year is 1992. Eugene Podkletnov, a Russian research scientist working at Tampere University of Technology in Finland, noticed something strange. He recounts his observations.
Someone in the laboratory was smoking a pipe, and the pipe smoke rose in a column above the superconducting disk. So we placed a ball-shaped magnet above the disk attached to a balance. The balance behaved strangely. We substituted a non-magnetic material, silicon, and still the balance was very strange. We found that any object above the disk lost some of its weight, and we found that if we rotated the disk, the effect was increased.
Podkletnov published a few papers on gravity modification starting in 1992, claiming it was possible to reduce its effect. However, as word got out about his research and controversy over the validity of his claims started to spread, Podkletnov's colleagues began to distance themselves from the research. Eventually, he was fired from the university. In 1997, Podkletnov claimed researchers at universities in Toronto and Sheffield were able to reproduce his findings. Later on, in a news piece published by the BBC, it was alleged that researchers at Boeing had begun work in secret on a black project called GRASP, or GRASP, Gravity Research for Advanced Space Propulsion, to develop gravity shielding devices using rotating superconductors. And in 2002, another article was published supporting Podkletnov's claims. Nick Cook, a reporter for Jane's Defense Weekly, alleges that Boeing, BAE Systems, and Lockheed all tried to approach Podkletnov directly. However, Podkletnov refused. Can we create artificial gravity? Is anti-gravity possible? Throughout history, humans have dreamed of defying gravity. From the myths of flying chariots to the futuristic visions of floating cities, the idea of overcoming Earth's pull has captivated the human mind. We appreciate all of you who have joined us so far on this channel. We hope you're as fascinated by these mysteries as we are. Please take a moment to subscribe, like, and turn on notifications. By doing so, you're supporting the educational mission of this channel and helping us create more inspiring science-focused content. Thank you. Podkletnov's findings related to gravitational shielding were met with both fascination and skepticism. Some saw it as a breakthrough, others dismissed it as an experimental anomaly. But what if he was onto something? Superconductors exhibit unique electromagnetic properties, including the expulsion of magnetic fields, the Meissner effect, and the quantization of magnetic flux. In the early 1990s, physicists named and Douglas Torr proposed that superconductors might also exhibit gravitomagnetic effects analogous to electromagnetism, potentially leading to observable gravitational phenomena. They suggested that a rotating superconductor could generate a gravitomagnetic field, which might be detected experimentally. Could superconductors hold the key to anti-gravity technology? To understand anti-gravity, we must first understand gravity itself. Einstein's general theory of relativity tells us that gravity is not a force in the traditional sense, but a curvature in space-time caused by mass. This fundamental understanding has driven physicists to explore ways to manipulate gravity. String theory offers a potentially deeper perspective, suggesting that the universe's fundamental building blocks are tiny, vibrating strings. According to some models, gravity may be weaker than other fundamental forces, because it propagates into additional spatial dimensions beyond familiar 3. If true, this could provide new pathways for manipulating gravity, perhaps even unlocking the secrets of anti-gravity. One possibility to achieve this may involve theoretical negative matter that would exert a repelling gravitational force. Could such exotic materials exist? If so, could they be harnessed for propulsion? Physicists have long speculated about negative mass. In certain theoretical models, if negative mass were to exist, it would react opposite to normal matter under force. Push it, and it accelerates toward you instead of away. In the context of general relativity, the existence of negative mass could lead to repulsive gravitational effects, potentially enabling anti-gravity propulsion mechanisms. This counterintuitive behavior could revolutionize space travel if we could find or create such matter. But where would it come from? Some scientists believe that quantum field fluctuations, the very fabric of space itself, could hold the answer. Quantum field theory suggests that space is never truly empty. Tiny energy fluctuations, known as zero-point energy, ripple across the fabric of reality. The generation of negative energy densities, as seen in certain quantum states, might produce repulsive gravitational effects. The Casimir effect, an observable phenomenon, demonstrates how quantum fluctuations can exert forces between objects. Could this mysterious energy be manipulated to counteract gravity? The Casimir effect arises from quantum field theory, describing the attractive force between two uncharged parallel plates in a vacuum, resulting from vacuum fluctuations. This phenomenon is a manifestation of zero-point energy, the lowest possible energy that a quantum mechanical system may possess. Some speculative theories propose that harnessing zero-point energy could lead to anti-gravity effects. But how do we test such radical ideas? Scientists are constantly probing gravity's deepest secrets. High-precision experiments, such as those testing the weak equivalence principle, seek out inconsistencies that could hint at unknown gravitational interactions. A single deviation from expected results could signal new physics, perhaps even undiscovered link to anti-gravity. Torsion balance tests and lunar laser ranging have tested the WEP to extraordinary accuracy, seeking deviations that might indicate new physics or gravitational anomaly. Recent studies have examined the effects of superconductivity on gravity. The London moment, a known quantum phenomenon in superconductors, suggests a connection between magnetic fields and spacetime. A rotating superconductor could be generating a corresponding gravitomagnetic field by frame-dragging spacetime. Could Podlatnov's experiment have been detecting an undiscovered gravitomagnetic effect? In the vastness of the cosmos, nature itself provides hints that gravity may not be as unyielding as we once thought. Dark energy, the mysterious force accelerating the expansion of the universe, acts in direct opposition to gravity on a cosmic scale. Dark energy's repulsive effect on the large-scale structure of the cosmos can be viewed as a form of anti-gravity. Understanding dark energy is one of the foremost challenges in cosmology, as it constitutes approximately 68% of the universe's total energy density. Could understanding dark energy help us unlock the secrets of anti-gravity? Even within theoretical physics, exotic solutions such as warp drives and wormholes propose bending or manipulating space-time itself. While these ideas remain speculative, they provide a framework for envisioning a future where gravity is no longer an obstacle. For now, anti-gravity remains a tantalizing mystery, a frontier just beyond our grasp. But history has shown that today's impossibilities can become tomorrow's breakthroughs. From the dreams of visionaries like Podlatnov to the rigorous work of modern physicists, the search for anti-gravity continues. Perhaps, one day, we will learn to master gravity itself and take our first true step into the cosmos, unbound by the limitations of our world. Stay curious, my friends, and remember, there's a whole universe out there just waiting for you. Yes, you, to explore it. See you.